Okay, now that we've worked and gotten this permutation property, let's get a payoff for it. Let's prove a theorem that's very interesting. It's called Fermat's little theorem. And what Fermat's little theorem says is something that's pretty surprising, actually. It says, take a prime number p, and then take any number that's less than p, that's not 0. Now raise a to the power p minus 1, and see what that's like mod p. And what Fermat's little theorem says is it's always equal to 1 mod p. Now, for you, I strongly encourage you at home to play with this and just have fun and explore lots of different numbers and see, when does it hold, and make yourself really believe it. But what I'm going to do is show you how to prove it using basically the permutation property that we had. So the first thing we're going to do is we're going to notice that here we have p minus 1 numbers. So let's call this the set S. Now, suppose I take the product of all the numbers in S. The product I in S of I. Right? What is this? Well, this is just p minus 1 factorial. Right? This is what you get when you multiply 1 times 2 times 3 times 4 times 5 times 6 all the way up to p minus 1. So this is a way of getting all these numbers multiplied together. I take p minus 1, I get p minus 1 factorial. Now, I want to use the permutation property. So what I want to do is I want to look at a times s. What do we mean by this? What I mean is the set you get by multiplying every element of S by A. So what is this? This is going to be defined as X is a member of A times S if and only if there exists a Y that belongs to S and X equals A times Y. So basically this is a fancy way of writing what you expect. A times S is the set you get by taking S and multiplying everything in it by A. So what's in AS? Well, it's the set A, 2A, 3A, all the way up to p minus 1 times A. I want to look at the set AS mod P. So what do I mean by this? I mean, I want to take everything in AS and I want to just mod it by P. So this is going to be A mod P, 2A mod P, 3A mod P, all the way up to P minus 1 times A mod P. Well, I know that A is relatively prime to P, because after all P is prime, it's relatively prime to anything except its own multiples. So that means that this is a permutation of S. It's just the same entries rearranged. I know that if I multiply everything in T together, I'm going to get the same thing that I get when I multiply everything in S together. It's the same elements. And that's true whether I multiply them together regularly, the way I did here, or whether I do it mod P. This has to equal the product of all the j inside T j. Again, where that multiplication is being done mod p. Why does this have to hold? Because it's the same set. By the permutation property. So now I know this is true because it's multiplying the same set, but I also have a different way of representing them. I know the first thing is equal to p minus 1 factorial mod p. But what do I know about the second? Well, multiplying all these things together is a times 2a times 3a times 4a times 5a all the way up to p minus 1 times a. So pulling all the terms out, I get a to the p minus 1 terms of a, times p minus 1 factorial, all mod p. Well, now the question is, can I actually look at p minus 1 factorial and can I divide by it? Okay, this is the key thing. Can I divide by it on both sides? Because if I could, then I'm basically done. Well, to be able to divide by it, it has to have a multiplicative inverse. For it to have a multiplicative inverse, we need to check that the GCD of p minus 1 factorial mod p and p is equal to 1. But we know that has to be the case. Why? Because p minus 1 factorial only has those factors, those numbers as factors which are less than p, but p is prime. So it's relatively prime to all numbers less than it. So just multiplying together a bunch of numbers that are relatively prime to p doesn't make a new number that's a multiple of p. So this is in fact true. Because this is true, we can divide both sides by it. And we'll get 1 equals a to the p minus 1 mod p. Which means that we have proven Fermat's little theorem.